As David said, I got here in 1952, and this is what the atmosphere in Los Angeles looked like then. You can see here where the pointer is. That's the Los Angeles City Hall. You can barely see it 3 blocks away. This, of course, was of great concern to the inhabitants of this region, and everyone was yelling and screaming and blaming somebody. But there was one bit of leadership, and that was Arnold Beckman. He had been a Caltech professor, and then his company, Beckman Instruments, got so big that he had to go over there and spend full time running it. And he founded the Los Angeles Air Quality Control District and set it up with a lab and fitted the lab up with all the most modern instruments that he had created in his company, like this one here. And he got his colleague, Barry Hagenschmidt, to come down for a year and finish. Barry had been thinking about smog and trying to figure out how it worked. And Arnold and he worked together and pretty much figured it out by the late 50s. He said it would take a few years before they could get cleaned up. Well, a few turned out to be about 50 years. But now we have clean air, and we can see the City Hall in Los Angeles. Arnold became a good friend of mine, and I must say, a great human being. Arnold, when he was a professor, had a grad student by the name of Bill Shockley. And after he got his PhD, Bill went back and worked at Bell Telephone Laboratories through World War II. And he and his colleagues here, just after World War II, invented this thing called a transistor. And we'll talk a lot about those tonight. They're an amplifying device that took the place of vacuum tubes. Many of you remember the vacuum tubes we used to have on our radios. In 1956, that invention was found to be worthy of a Nobel Prize. And after getting the Nobel Prize, Shockley went to his old boss, Arnold, and said, "I'd like to start a company to manufacture these transistors." And Arnold said, "Okay, but why don't you make it a division of Beckman Instruments?" And they agreed. Here's their agreement. And so the Shockley Semiconductor Laboratory, part of Beckman Instruments, was set up in Mountain View, California, right next to Palo Alto, where Shockley had been raised. Well, Shockley needed people for his company, so he went on a trip to the East Coast. And of course, he was in great demand to give talks, what with this new device and his Nobel Prize. So he went around giving talks and recruiting the brightest people that he could find that were working in areas that were related to what you do to make transistors. And here that group is celebrating Shockley's Nobel Prize. The party didn't last long. Turned out Shockley was a really very good scientist, but he had zero management skills and zero people skills. And in less than a year, he had alienated almost everyone in the group. So 8 of them, which Shockley called the traitorous 8, went to Arnold and said, either Shockley goes or we do. And Arnold couldn't find it in his heart to fire Shockley. It's a decision he regretted all the rest of his life. He shared his regret with me on a number of occasions. So these people went off and they got Sherman Fairchild to fund their new little company, which is Fairchild Semiconductor. Turned out to be the most important company of the 20th century. Some names, Shah-Herney here and Bob Noyce, I'll mention later. Gordon Moore, Caltech graduate, and I became close friends and working colleagues and, for many, many years. Many years later, we had a chance to reminisce, and I thought you'd like to hear what Gordon thought of all the things that happened in the early days. You and I met around 1960.
It was earlier than that.
59, probably.
Carver was a professor at Caltech. I was going down there, and I walked into his office, and I think I asked him if he could use any transistors. Was it?
I was teaching a undergraduate course in transistor electronics at the time, had a lab with it. So, and of course, trying to teach people how to use these things. So that was a no-brainer.
Yeah, I had a couple of big envelopes of what we called cosmetic rejects. They didn't look good, but they still worked. And I guess I populated your laboratory for a few years with those.
We had a lot of very good projects come out of the lab because of those transistors. That was great.
Well, these are the transistors that Gordon had given me. This is what's inside one of the little cans that you think of that have the 3 wires coming out of it. This is the place where you can bond wires to go to the little wires that come out of the can that transistor was in. One there, and then this piece of silicon, which is about the thickness of a thin piece of cardboard. Started out as a wafer round slice that had several hundred of these on it, and then they were scratched along the boundaries and broken apart. And so you had individual transistors. And in 1958-59 timeframe, a fantastic thing happened. Shah-Herney, whose picture you saw, figured out a way to make another layer underneath this transistor so that this electrode here wasn't just the piece of silicon that was down where all the transistors were, but each one was now separate electrically. And Bob Noyce took one look at that and said, that means we can make a complete circuit by just using this aluminum metal, this white stuff here, to hook the transistors together in the way we want them. And then instead of a transistor on a piece of silicon, we will have a complete working circuit. This was the most important invention of the 20th century. Well, once people got onto it, they began to think of more and more useful circuits. And so they began to put more transistors, hook up with more wires, and these are done at about 1-year intervals. And so 5 years later, this was the complexity of the circuit. And Gordon, 5 years in 1965, wrote this wonderful article in Electronics magazine predicting that this trend to make more and more complicated circuits was going to continue. And we had many discussions about it.
So then we started working together in various ways. I remember coming up essentially every week and visiting you at Fairchild. Lots of good discussions. There was one particular discussion I remember vividly about when you asked me how small a transistor could get. You remember that?
I remember it rather vaguely, but I know you went away and figured it out.
I spent the next 20 years of my life following that thread. So.
Well, what I had figured out was at a talk I gave in 1968 at a little IEEE workshop. Here's a cross-section of the transistor. Here's the region called the emitter that has lots of electrons in it. And here's the gate, which is insulated from all of this stuff down here. And here's a thing called the collector or the drain, depending on exactly which kind of transistor you have. And I did a very simple analysis. What happens if you take one of these things and shrink all the dimensions and also shrink the voltage so that the electric fields are the same? What happens? Well, what happens, of course, is you get, let's say you shrink it by a factor of 10, well, then you get 100 times more transistors on a square centimeter. But because the transistor is shorter path that the electrons have to go, they get there half the time. So the transistors switch twice as fast. So the amount of computation you get on a square centimeter of silicon went like the cube of the scaling factor. It was fantastic. Well, when I gave this talk, of course, everybody yelled and screamed at me because it couldn't possibly be that good because of something you left out and all of the typical things that you get. But it turned out that that's pretty much what happened. And then as to how small you could really make them, the physics that would limit the size is the thickness of this gate oxide here. And there's this phenomenon of electron tunneling that if you make an insulator thinner and thinner, the wave function of the electrons on one side will die out exponentially in the insulator, and a little bit will get through, and so the electrons will leak through the insulator if it gets too thin. Well, we had done a lot of measurements on very thin insulators, and here's the rate at which the electrons seep off due to the electron tunneling. And even down at 3 nanometers, which is kind of dimensions that people talk about in today's integrated circuits, it only took 10 to minus 5 seconds. Well, you think that's pretty fast, but transistors that small will switch almost 1 million times that fast, so the leakage isn't going to affect the performance of the circuit hardly at all. So that was the thing that gave us great confidence that you could go many decades in the size of the transistors that made these integrated circuits. So here we were down here in 1968, and we had said you could get 100 million transistors on a square centimeter. And then I became an evangelist for Moore's law, which is this exponential increase in the number of transistors on a chip. And after a while, it sort of became a self-fulfilling prophecy. And we got up to the 100 million, and around 30 years after I'd made this prediction. And if you think about it, that's a long time to be predicting an exponential. So Moore's law became the thing that built the information technology that we have today. And it was great being in the thick of it. And right up here in 2005 was when Gordon and I had that little session where we were discussing the history. Well, another thing happened. We're back here in the story in 1968. And another thing happened in 68. Bob Noyce and Gordon Moore decided to leave Fairchild Semiconductor and start a company to just do integrated circuits. And they asked me if I'd like to come along as a consultant and help out with their starting a new company. And of course I said yes. And that gave me a chance to look at how they were designing these integrated circuits. And this is what they were doing. Here's the drawing of the pattern that makes the circuit like we saw in the little ones. And what they drew on the Mylar was all 4 or 5 layers of the process that were sequentially done to make the actual circuit on the actual silicon. Well, in order to form those patterns a layer at a time, you need a mask for each layer separately. So they put on top of this drawing a sheet of this stuff called rubylith. It's just a Mylar sheet with a very thin coating of almost transparent red material. And it's thin enough that you can cut through it with a very sharp knife blade, which is here. And this machine is set up so that you can lock the X coordinate and then move it in Y, or you can lock the Y coordinate and move it in X. So you can cut out little rectangle shapes. And then when you've done that, somebody else comes along with a pair of tweezers and carefully peels out the red that you don't want, not disturbing the red that you do want, because that's the pattern you want to make a mask for. It was nuts. It was stark raving mad. Here, we were going to have things of the 100 million transistors, and you were going to draw it by hand and then cut out all the little shapes with these. No way. So, as they did it, in fact, then Gordon made a slide after a few years of how many people months it was taking to do this. And it was going up here, it was headed for the moon. And there had to be a better way. So I spent all my not spoken for hours trying to figure out a better way. Well, there was only one way. There's only one technology that had the property that the precision didn't get worse when you made the thing bigger and more complicated. And that was a digital computer. So there had to be a way to make a pattern with a digital computer. And it turned out there was this thing called a Gerber plotter, which plotted on sensitized film, big pieces of film, and made shapes that were exposed on the film. And then that could be reduced down by the mask house and turned into a mask, just like they were doing with those rubylith shapes that I showed you. You also had to think about how you were going to design the thing, because you didn't want all these little random kind of shapes. You wanted something that was a sensible program that you could write to generate the shape. So this is an example of one such thing. This area here consists of 2 planes, I call them. This one takes inputs along in the bottom here, and they run up on wires through here, which are the gates of transistors. And then the outputs run along here, and they go into another such plane. So this computes a NOR function of the inputs that are connected to it. And the same thing here. The inputs go along here, and the outputs go vertically. and the outputs are connected to the ones you want. So you can program this thing with one mask that just makes a contact or doesn't at each of these transistors. So it's an orderly, systematic way of doing design. And it turns out if you hook the outputs, so these are little storage devices, so they store the bit and feed it back around. So it's the input to the next cycle. This then becomes what was called a finite state machine. It's a general sequential logic thing. And it was known in computer science then that if you have a finite state machine and you can have a memory with it, which is what this little thingy down here is, that's a general purpose computer. It'll compute any computable function, limited only by the size of the memory and the number of operations you can do with the finite state machine. Well, I programmed this to do a 12-hour clock because that was a simple way that you could find out if it really worked, because it has all kinds of special cases that 12 goes to 1, and it's all funny. A standard binary counter doesn't do what a 12-hour clock does, so that was a good test. So I got my program, did all this programming on punch cards in the Caltech Computing Center, and they had a way of creating a paper tape, and there was a place down in El Monte that had a Gerber plotter that I could just pay the man to make plots. So he made the plots for the 5 layers in the process for this chip, and I took them up to Intel. At that time, Jerry Parker was in charge of the reliability for Intel, and so he could run test chips through the process, and this was just another test chip. And Jerry was a former student who is now a Caltech Distinguished Alumnus. And so I got these chips back, and this thing is a package, and I put the chip, there's the chip there. You get the scale, this is my thumb over here, and the distance between these pins is 1/10 of an inch, and those pins go down into the plastic. And you can hook wires to them, you can put them on a circuit board. So this is a way of getting at the contacts to the little chip itself. So for example, if you want to hook that bonding pad on the chip up to this thing on the package, which goes underneath, comes out to that pin. And so you can put it in a circuit board or put clip leads on it or whatever you want to do. So I got a bonding machine that I figured out how to work. I was doing all this on my own nickel, of course, because there's no support for anything like this. It wasn't real research. And so here you go. You bond that little wire. That wire is half the size of a human hair. And then you bond it up there, and you do that to all of the pads. And that's just one of the things you do. If you're going to make integrated circuits, then you have to be able to hook things up to them. Well, that was my first chip. There's a nice movie on that on my website. And the students found out about this, so they wanted to do it, of course, because they knew where the future was going to be. So this is the first class, 1971, and here's half of the class. And they would write programs to create their little project. These are each project of a separate student. And this is one of the pieces of photographic film that the Gerber plotter had plotted these on. There were 4 or 5 of these for the process we were using at Intel. So I took these up to the mask house and got masks, and by then I think Ted Jenkins was in charge of fab for Intel, so he started running these class chips through, and this is what the first class chip looks like. You can see here 1971, and here's 1972, and you see we're getting better at it. We're getting more variety of more inventive chips on these multi-project chips. Of course, you can't have a run through the fab for every little project, so you put them all on a multi-project chip like this. And by 1973, you can see here's the class chip for that year, and we have some grad students that were now doing thesis work by exploring the space of, instead of making microprocessors that just did one thing at a time, they would do very parallel computing so that every place on the chip was doing a bit of computing every clock cycle. And that became a goal for the kind of chips we would like to make, that every bit of the silicon was working all the time. And it's amazing how many things you can do that come out that way. Well, about this time, here's Dave Johansen doing a thesis project. And what the thesis project was a program that we called a silicon compiler. And what you put in as a user is you put in the definition of the instruction set that that computer would do. And the program, Dave's silicon compiler, generated all of the design that they were doing with their little marks on Mylar. It generated the entire thing, and the user didn't have to see any of that. They just put in what instruction set they wanted. It was light years ahead of anything industry was doing. Well, about that time, Ivan Sutherland came by, great guy, and we hit it off real well. So he joined our faculty, and they gave us the job of starting a computer science department, as if we didn't have anything else to do. And we did. And it was the only computer science department in the world where people learned how to design the computing machinery that actually did the real computation physically, and then also all of the software that it takes to make a modern computer environment. Well, it turned out Ivan had a brother, Bert, who was in charge of the computer science part of Xerox Palo Alto. And Xerox Palo Alto was known in those days as the hot place in computer science. And so I was very happy to meet Bert, and Bert said, "Hey, that's good stuff. Will you come up and give us a seminar on that?" Sure. So I did. And after the seminar, Bert introduced me to this lady, Lynn Conway, and she had a computer architecture background, so we had a good mix of talent between the two of us. And she said, you need to write a book about this. And I said, well, it's not like I have a lot of free time. If you think that's a good thing, why don't you become my co-author and we'll do it together. So we did. And by 1978, we had the first 4 chapters, and Lynn made a bunch of preprints of that we gave to people that were starting to teach this class at other universities, and one at Carnegie Mellon and one at Berkeley, and then Lynn took it back to MIT and taught a course back there. So it's starting to get out. But in 1979, a big thing happened. Lynn made a big printing of the first bits of the book, and she had put together a group of people to automate all of this thing of placing the student projects on a multi-project chip and figuring out how to bond them into packages. And it turned out by then that the Mask House had their own pattern generator, so I didn't have to go to El Monte and get somebody to run a Gerber plotter. So they started out making a conversion to the language that the pattern generator in the Mask House had. So you could, instead of giving the Mask House these big pieces of film, you could give the Mask House files. And this group that created this is a great group of very smart people, some of whom are from here. One in particular, Dick Lyon, is here with us tonight, and has become a lifelong colleague. Well, Lynn gave these books out to people at all the universities who showed an interest. And they sent their files, which defined their geometry, in over the ARPANET. Lynn had arranged to allow that. And then the little group in Lynn's operation did all of the work of getting the files to the Mask House and getting the mask made. And then a neat thing, an old friend of mine from Fairchild, Pat Castro, had gotten in charge of the wafer fabrication for Hewlett-Packard. And they agreed to do the fabrication for this run. And they found a way to get them bonded and packaged and back to the users, and the whole thing in a month. So this became the model of how modern places do design of integrated circuits and send them to a fab, and it gets fabricated and sent back to them. So it was a great send-off, and I didn't have to do it anymore. It's great. I was burned out by them. The book came out in hardback that year, 1980, and then people started to notice this was an important thing, and we got this electronics magazine thing, and off it went.
One of the most important things for the industry overall was actually a book that Carver and Conway
Lynn Conway
wrote on systematic design of CMOS circuits. Now, it trained a whole generation, at least a generation of engineers who came out of school finally knowing how to design integrated circuits. Carver's design technology certainly ended up, I guess, spawning the custom integrated circuit business and continuing to nurture it. But systematic design, a variety of different approaches, has got us off that curve that was growing to the point where we wouldn't be able to design the products we make today at all.
Well, the products they were making were these microprocessors. And it was going on Moore's Law. They were growing exponentially more complicated. But they were still microprocessors. They just do one thing every clock cycle. And that's not the best you can do with silicon. There are applications which require a lot more of the silicon to be working a lot more of the time. And I'll show you a couple of examples. Here's my friend Marty Cooper, who was in charge of the communication systems part of Motorola at the time. And he has this thing in his hand called the brick because it was big and heavy. But what it is the first cell phone. And here he is on the streets of New York calling his arch competitor at Bell Laboratories and telling him he's been scooped. It was a great time. It took another 10 years or so before they could make custom integrated circuits and make a much more capable phone in a much nicer package. This little razor phone I carried for quite a number of years and was very fond of it. And that started an exponential in the use of cell phones in the US. And after a few years, everybody had one. And that kind of computation was what you did with custom integrated circuits that you could now get fabricated. And you all probably have a screen like this in your car and also in your cell phone, and it knows where you are. Well, how in the world would it know where you are? Well, it knows where you are because it's a GPS system. Well, what's GPS? Well, GPS has a bunch of complicated signals that are sent from space, custom satellites, and it was designed for the military to do what they do very precisely. Well, the codes that they used were secret, and you didn't have access to them for commercial purposes. But Charlie Trimble figured out that he could just listen to a bunch of those codes and analyze them and figure out what to do himself without any knowledge of any of the secret stuff. And this is the very first commercial GPS. And here's Charlie years later giving it to the Smithsonian because it's a historic thing. And here's Charlie a few years ago getting the Von Karman Wings Award, which is the highest honor you can get in the aerospace industry, because of course you can't make a commercial flight without GPS. So we have one Caltech person to thank for having GPS on everything we do. Charlie was an interesting student. He has a vision problem, can't see very well at all, so he always sat in the front row. And he would often come up after class and ask questions, and they were always really good questions. And Charlie's gone on to do the Trimble navigation, and he's now a Caltech trustee and helps young people getting their projects going. Wonderful friend of Caltech and personal friend of mine. Well, you don't just need to process information to have an information age like we're in. You also need to ship information from one place to another, and as you all know, the World Wide Web goes worldwide. So you have to ship data all over very long distances. Well, how does that work? Well, most of the data are carried on fiber optics. The way fiber optics work is if you take a cross-section, it's a silicon oxide fiber, but it has in the middle a little core that's formulated a little differently so that the light in the core propagates a little slower than the light out in the gray area here. Well, that has the effect of, as the light goes along, it tends to self-focus, so it doesn't spread out and get lost, and it can go hundreds of kilometers. But in order to carry data, that light has to be very precise frequency, and then you change the phase of the light, and that carries the information. So the light has to have a very stable, very precise frequency. Well, the first step in getting light like that was, of course, a laser, because that's what a laser does. It gets coherent light that's all the same frequency. But the very first lasers that were invented by Bob Hall, Caltech graduate and working at GE Research Lab, a great guy. He used to come by every year and give a seminar, and wonderful fellow. And his invention was you take an ordinary PN junction, just a plain old diode made of this gallium arsenide material, and you polish the front side here and the back side around that we can't see, and you have to polish them so they're absolutely parallel, and then the light can bounce back and forth, and it has a resonance, and that fixes the frequency. That's what makes it a laser. Well, that was a good start, but those lasers, very hard to get yield on because you had to get everything so precise, and also they weren't good enough to really couple the light into these optical fibers. So my good friend and colleague Amnon Yariv, right here at Caltech, said, if you want a very precise, Amnon's with us tonight. If you want a very precise frequency, very precise wavelength, you just put little bits of impurity on a pattern that has exactly the wavelength you want the light to be, and then no light that isn't that wavelength can propagate there. So wonderful insight. It's the laser we still use for the World Wide Web, and of course Amnon's still making better lasers. Result of all this is that we have a World Wide Web that's carrying more and more, exponentially more data all the time. 2 Caltech people in a row it took to do that one. Well, you can process information and you can ship information from one place to another, but you also want to be able to use that information to do work, to turn on lights and to run motors and that kind of real work in the real world. And that takes more than information. It takes energy. It takes power to run the motor or run the light. And no surprise, the field of power electronics in the modern age, using this very capable, very fast semiconductor technology that we've developed for information. And there's been a slower but also remarkable evolution of power devices using semiconductors. And how you do power control with those devices was developed right here at Caltech. This is David Middlebrook. He was my thesis advisor, an excellent advisor, wonderful teacher, crisp, perfectly logical development of everything he did. And later on in the 70s, he had another graduate student, Slobodan Chuk. He's here tonight somewhere. And together, they figured out this field of power electronics. And Slobo's thesis, even today, reads like a textbook on how you do power electronics. It's a marvelous thing. Well, one of the great things that happens when you have a new field that you're building in a university is you get students that just get it and go with it. And in their case, the student that really got it and went with it was Alan Cocconi, who got his degree in 1980. He was unwilling to go to work for a big company because he wanted to do power electronics. And so he had a friend at a company called AeroVironment, and you know AeroVironment because of, it was started by another Caltecher, Paul McCready, and they do fantastic aerodynamic structures. They're very lightweight. This is their Gossamer Albatross that you all read about, that one person pedaled across the English Channel. It's fantastic. Well, they got a contract to do an even more demanding design, and that is they wanted to make a flying replica of the largest creature to ever fly. And if you're going to do this, you have to have really good aerodynamics, and you have to have really lightweight structures, but you also need power electronics. So they hired Alan Cocconi as a part-time consultant, and he built the power electronics for the Petrodactyl. The next project they had was this one.
On November 1st, 1987, the World Solar Challenge, the first transcontinental solar car race. Powered only by electricity generated from sunlight, these racers were attempting to cross an entire continent through the desert and the desolate outback to reach a finish line in Adelaide, almost 2,000 miles to the south. The saga of the Sun Racer had begun less than a year before the car crossed the finish line. The first step was to test a quarter-scale model at the Caltech wind tunnel.
Basic drag that we measured was 0.09 drag coefficient, straight ahead flow, which made us very happy. It was right where we wanted it to be.
But construction and assembly took place at AeroVironment's Simi Valley facility. This 15-pound frame would support a total weight of 570 pounds. The Sun Racer's revolutionary motor was designed by General Motors Research Labs.
It was a good opportunity to use a new magnetic material called MagnaQuench. Our motor ended up at about 92% efficiency.
Hughes designed and built the solar array system. This array would have a peak output of 1,500 watts. In just 6 months, we had designed, built, and test-driven a prototype of the car, which set the world's speed record. Before we knew it, we were on our way to Australia for the real race, the World Solar Challenge. First driver, John Harvey, flew off at 60 miles an hour, leaving the others behind. The Mauna Loa from Hawaii gave Sun Racer a good chase. It was followed closely by the Swiss car, the Spirit of Beale. By the end of the third day, Sun Racer was more than halfway through Australia and the race. It was 310 miles ahead of the Spirit of Beale. When the Sun Racer crossed the finish line, the second-place car was 623 miles and 2.5 days behind it.
We've been delighted to see the tremendous use of technology in Sun Racer all happen because of all the people that made it happen.
Well, the people that made it, Alec was a project manager for the Sun Racer, and he and the crew there that had done it knew they could make a real car from where they were with the Sun Racer. And so they went to General Motors and they said, fund us for another couple of years and we'll make a prototype of a real car that runs on electricity. And they did. This is a thing called the Impact, and it's a beautiful device. And peppy as can be, the electronics were just like a modern electric car. Well, that was impressive. Here it is up here. This is the impact. It says so right there. And General Motors decided that was really good. Let's make a production car. So they did. They put together a whole group of people in General Motors. Of course, they didn't feel like AeroVironment was up to the task of doing a production design, but they did let Alec consult for them in the process, and he made sure it came out okay. And that was the EV1. And there's one right outside, that nice little red car that you see out there. It's kind of sad. General Motors leased these cars. They didn't sell them. And they had over 1,000 of them out, and people loved them, but General Motors had a new management come in, and they looked at it and they said, this isn't making any money. And they canceled the whole program, and they recalled all the cars and crushed them. And you've all probably at least heard of the little movie, Who Killed the Electric Car? You can find it on the web. Meanwhile, there are other people in AeroVironment that weren't any part of this effort, and they decided they could do something on their own. So Alan Cocconi came up with some money he'd saved up from his consulting, and Wally Ripple, who's here tonight, and you'll see him out with the cars outside. Wally had done a lot of things with electric cars and spent quite a number of years at JPL studying electric vehicles. JPL has some interest in things that run on electricity, as you might guess. And they started this little company, AC Propulsion. And they were making what they call drivetrains. A drivetrain is a power electronics and a motor that's optimized for working with the fast switching signals that you get from power electronics. Wally was an expert on motors and can give you a long description of what the best way is to run a motor. So once you have a drivetrain, all you have to do is put a car around it, and then you've got an electric vehicle. So, well, they weren't getting too much business for their drivetrains. And finally they said, look, we're not going to make a dent in anything unless we make a car that just blows their socks off. So they did. They made this little baby. It was just fantastic. It would beat any gas car in the quarter mile, and it had 300 miles range, and just a fantastic experience. And it did blow people away, including Elon Musk, who said, yeah, that inspired the Tesla Roadster, and without it, Tesla wouldn't exist. It's also a nice-looking little car, and a lot of the design work was done by Scott Sorbet, who's here tonight and has brought his T0 so you could look at it. It's outside. There's only 2 of them, so we owe Scott a big favor for bringing his car in so we could look at it. Well, that brings us up to the present. There's one other technical thing that's in the press a lot, and that's AI, artificial intelligence. And as Yasser Abu-Mustafa, our local expert here, told you in his own Watson lecture a few months ago, highly recommended. The technology is neural networks. The result, if they're smart enough, is artificial intelligence. And Yasser's literally written a book on the actual, real details of what makes these things actually work. And he teaches a class every year. And that class is on the web since 2012. Learning from data. By now, he has educated millions of students in how neural networks work. But if you think about it, a neural network is a program, and it has to run on silicon chips somehow. And they were going along pretty well. This is how much computing it takes to train one of these things as a function of the year. And this line down here is Moore's Law. Moore's Law looked steeper when it was on those other plots, but if you look at the number of zeros, these are many times steeper than Moore's Law. So this isn't because of Moore's Law that we can actually run these programs. Somebody had to make chips that were better than computers. Ordinary microprocessor, not even close. Well, that person was Bill Daly. He was here at Caltech during the great days of VLSI and all of the thinking that was going on and how you make things that operate in parallel over the whole surface of the silicon. Right here at Caltech in '78, there was a Caltech conference on VLSI, and H.T. Kung from the class in Carnegie Mellon had invented this two-dimensional way of doing multiplies that are needed for these neural networks. And Bill was able to get all that stuff on big, capable chips. And his company, NVIDIA, I think you've observed, has become one of the foremost companies in the world. And their president, Jensen Huang, will be our commencement speaker this year. So Caltech, once again, has keeping things at the leading edge. Well, if you think about it, a neural network was supposed to be looking at the brains of animals and seeing how they worked and seeing if we could find something interesting that we could do with our electronics, not the gooey stuff that goes on in the brain, but on silicon. And could we adopt some of those techniques to make better computation? And what neural networks did was they learned one thing from the brain, and that is how to learn. And that's important. And as you can see, you all have programs that will talk to you and create documents for you and all of that, which we didn't have before. But it's one idea. You learn from stuff that's computer readable. There's more that goes on in the brain than that, and that's coming along too. Back in 1980s, we had a biology student, Misha Mahawalt, fantastic, talented student, and she was studying the visual system of animals. And she looked at the way the visual system works, in particular the retina. The retina is a little piece of the brain that's grown out just behind the focus in your eye, right at the image plane. And it does some kind of computation on the data that's sensed by the photosensors in the eye. Well, what's that about? Well, Misha figured out what they were doing, and she said, you guys are doing something that's really stupid. You have this thing you call a television camera, and what it does is it goes and measures light at the first pixel and sends it out, and then the second one and sends it out, and the third one and across the row, and then it goes to the next row and does the thing. 1 pixel at a time until it gets a whole frame. And then if you want to see if something interesting is happening, like there's something moving or changing its color or whatever, you do it again and you get another frame. And then you put those in memory and you get some computer to go step at a time and compare the two and see where they're different. That's the dumbest thing you could do. If you're looking for a change in the image, why don't you just have a little circuit right at the pixel, which looks at the space-time average of the pixels around it, and if it's different, it tells you right now. Don't have to wait for a frame to come out and another frame to come out. Well, turned out that was a really good idea. But nobody paid any attention because they had their television images and they were used to working with them. But then people wanted to do autonomous vehicles. And you don't want to wait for 2 frames and for some computer to paw over them if you're driving down a dimly lit street at night. So here's a comparison with a picture that you get out of a television camera. This is, by the way, Sony, leading company in the imaging business. So here's a good imager that's television, and this is one of Misha's style, 30 years after Misha did it. Now it's being used for computer vision, where you want to see what's happening right now. And if you don't, you might run over it, and that would be a bad idea. So, once again, here's a young person that looked what was going on and said, that doesn't make sense. There's a better way. Figured out the better way. Made a device that did it the better way. Demonstrated that. And that put in place a process that now this technology is out making the world a better place. So, for the young people here, the reason I told these stories is you hear all the time all the problems with the world. But actually, what we have is a huge amount of technology that makes the world a better place, that's happened, that I've watched happen. And it's been exhilarating and exhausting and remarkable. And I would say to the young people, you know, a lot of people think that we've done it all. Don't even go there. Don't even go there. There's vastly more potential in the future than ever has been. Well, why is that? Well, we have this incredible technology that we can use to innovate with, vastly more than we ever had. And it's hugely more opportunity than there are problems. Don't wallow in the problems. It doesn't get you anywhere. Seize the opportunity. Go for the potential. And go out, find a better way, make it work, and make the world a better place. Bless you.